Sorry, you're on mute. If you're speaking, we cannot hear you.
Okay. May I start from the beginning or just continue? Okay. Social media platforms provide an incredibly rich source of real-time and user-generated content, making them invaluable resources for sentiment analysis. And on this slide, we see why we will stick during our research to the Telegram posts, because it is the main source of data, of news, and the main channel of communication for today's people in Ukraine. And let's talk a bit about the research gaps in this field. There exists a significant imbalance in the NLP resources available across different languages. While sentiment analysis for English has achieved remarkable accuracy rates exceeding 90% on public benchmarks, many other languages remain underrepresented in this field. This disparity is particularly evident in low and mid-resource languages like Ukrainian. The Ukrainian NLP community currently lacks a high performance and, importantly, open source sentiment analysis model comparable to state-of-the-art solutions available for other high-resource languages, not mentioned English. Our research addresses this gap by proposing a comprehensive approach to developing such a model, specifically designed for Ukrainian social media content. The main hypothesis driving us is that by combining advanced transformer architectures with appropriate processing and comprehensive training data, we can develop a model that achieves performance comparable to peers in high-resource languages, targeting accuracy rates about 85% or more, while maintaining robustness across different forms of Ukrainian language usage. And to ensure a comprehensive and systematic approach, we employed massive literature review and a citation network analysis. This methodology allowed us to discover pertinent literature by iteratively examining citation networks, starting with the seed papers, which we find on open databases, especially Google Scholar and OpenAlex, using combination of words like sentiment analysis, social media, low resource languages, Ukrainian, and multilingual sentiment detection. We identified 9 key papers that served us as starting points for further selection process. And these seeds ranged from fundamental works in the field, from such works to researchers focused more on Ukrainian sentiment analysis. And the key observations are, firstly, we keep our attention on works describing solutions for the Ukrainian language. And we find 7 relevant papers, including ones from the seed set, and found out that there is no publicly available code or data, so we cannot make a comparison or have a benchmark or a starting point for our research. However, there are good examples of commercial solutions on the market, and it shows that our research goal is feasible. The second key observation is that the most significant breakthrough came with the introduction of transformer architectures, especially fine-tuned BERT models, and their variants have achieved state-of-the-art results across various sentiment analysis tasks. These models serve as the primary or baseline approach in most surveyed studies that we include to our review. The self-attention, I think that the reason is that the self-attention mechanism in transformers allows these models to capture long-range dependencies and contextual information more effectively than previously existing approaches. Additionally, transformer-based methods can handle cross-lingual sentiment analysis, making them particularly valuable for our research or for environments like Ukrainian social media. And last but not the least, more recently, large language models like GPT, Gemini, Llama have introduced new possibilities for sentiment analysis. Their key advantages include deeper context, understanding, ability to easily handle long text, and complex linguistic patterns, including emojis, for example. And but however, these models face challenges also. And I think, yes, we have an example. Faces challenges in large-scale applications. They can show inconsistent performance across different languages, domains, and introduce biases in sentiment classification, as we can see on the slide. I take the title from one good article about comparison of modern LLM performance on niche tasks versus smaller specialized models. And the result from that paper tells us that the specialized models have not been dead yet, especially when we talk about sentiment classification. And the picture is from another good article showing the class distribution of GPT 3.5 versus human validation during the annotation process of social media text, considering the war in Ukraine. And we see the skewness toward negative demonstrated by GPT. Okay, let's move further to the methodology. Based on our literature review and gap analysis, we have developed a methodological approach that addresses the challenges. For our model architecture evaluation, we will test 3 approaches. What can work well, from our opinion, for these tasks. First, we will establish a baseline model using general purpose LLM with only prompting as a reference solution. Second, we will fine-tune pre-trained transformers from BERT family. Specifically, in the shortlist, we will work with Ukur Roberta, which was specifically pre-trained for Ukrainian texts. Modern BERT, a multilingual model optimized also for various languages, and XLNet as a state-of-the-art after aggressive model demonstrated for now in English, but can be also pre-trained on Ukrainian. These models have demonstrated have examples of strong performance on low resource tasks when fine-tuned properly. And the third approach, we will explore fine-tuning large language models, specifically GPT-4o, as well as Mistral, which has shown promising results for low and mid-resource languages in recent research. In case of Mistral, there are already pre-trained for Ukrainian language version of this model and available in open source. Let's go to the evaluation. We will use classical metrics while accounting for class balance in our dataset. This includes F1 score, which is the most popular metric for sentiment analysis in current literature, along with accuracy, outcroc, and confusion matrix analysis for different classes. We will also assess the reliability of our solution, final solution that will win in the competition of 3 approaches we demonstrated earlier, using expected calibration error. The key idea here is to evaluate how well a model's predicted probabilities reflect the true likelihood of an outcome. And this will show us how calibrated the model is. And we can move to the datasets block. A critical component of our research involves analyzing existing datasets and determining their suitability for the task. We collected 5 ones that could potentially support our work, spanning the years, the data in this dataset, spanning the years 2022, 2024. Most of these datasets aren't publicly available and were shared by other researchers from the Ukrainian NLP community. And our analysis leads to a clear conclusion that none of these investigated datasets are fully applicable to the problem. The primary limitations are either inappropriate language distribution, inapplicable sentiment orientation in annotations, or insufficient size. This justifies our decision to create a new dataset that properly represent the linguistic landscape of modern Ukrainian social media. Our initial version will include 4 sentiment classes commonly defined across existing research. There are positive, negative, neutral, and mixed sentiment. This classification schema effectively covers all possible emotional states without introducing excessive granularity when we talk about document level of research in sentiment analysis. And for annotation quality assurance, we are implementing several best practices from the literature. For example, to ensure consistency across different annotators, because we have invited 4 annotators and they agreed to join our project. So we need to ensure consistency across their annotations. We're employing inter-annotator agreement metrics, such as Cohen's kappa, and designed structured questionnaires that clearly define sentiment in each presented category. And if you want to, you can join this project also. As a tool for annotators, we have developed a Telegram bot providing a detailed guideline with examples. The key approach to the annotations here, to not deeply go in details, is to classify text by identifying key phrases or word combinations, but not relying on the context in our heads to make it possible for the model to capture the signal. And our early results, so far we have implemented the first 4 steps showed on the plan: review of the existing research, the exploratory data analysis of available data sources. We have annotated enough number of texts. For now, we have about 10,000 of annotated examples, and prepared the baseline approach. On the bottom part on the slide, we can see the results. Baseline approach is based on GPT-4o. It is clearly rely only on prompts, and we tested 3 different strategies: zero shot, few shot strategy, and chain of thought. And we can see that in case of GPT-O, zero shot strategy performs the best. As for the next planned activities, we will discuss the result in the future work. And for now, I think we are ready for questions.
Thank you, Yuri. Okay, we'll start from the audience.
I wanted to ask regarding your early results. Do you have some hypothesis ideas why zero shot performed the best on GPT 4.0 and why chain of thought, like in case with NER, I guess was the same thing, like chain of thought performed the worst for some reason?
I think it comes from the diversity presented in the dataset, because here a chain of thought based on 3 steps. The chain is always 3 steps. It includes the first step is to ask the model about define. During this experiment, we tried to reflect thoughts of annotators when we work with them while sharing our guidelines. Firstly, they read the text and try to define negative phrases, ask yourself about, are there any negative phrases in this text? The second question, are there maybe some positive part of this text? And the last question is, and based on the all information above make the most confident prediction about the sentiment. And I think that such an approach in case of modern LLM is quite unstable, and maybe some extremal cases or uncertain cases, chain of thoughts may introduce bias that lower our metrics. So this is my main hypothesis that can describe these results. Few shots, maybe a little bit similar explanation about it, also a little bit lower than zero shot. A few shots, it includes 10 examples about before we start annotate our data set, we find the most challenging 10 examples based on our opinion that hard to distinguish easily, and include it in the system prompt and push to the model every time it makes prediction.
Okay, I see we have a hand raised. Mariana, please.
Yes, sure. Thank you so much for the presentation. I have a couple of questions about the dataset that you're working on right now. You mentioned that you are re-annotating existing datasets. Which datasets are you re-annotating out of the list that you showed previously?
We include the data from all of them, but meanwhile maintaining the distribution of languages according to the current the most modern societal questionnaires. Around 20% of people in Ukraine read the content on Telegram or other social media in Russian, and all 80% in Ukrainian. So this is our benchmark for language distribution. So this is the main criteria how we pick, we formulate the final data set and prepare the annotation.
So in general, because these sizes are quite different, like we have on one end, we have like 564 text, I guess, posts, snippets, something, right? Items. And then on the other hand, we have 276,000 posts, which are 98% Russian. So I guess what is the end goal? Maybe that's my question, to cover all of them but with the language distribution, or how do you formulate the end goal of this annotation?
I think they cannot physically cover all of them because the last one is introduces too large bias. But for now, if we follow the link, the bot continues to work. So the data set, I think, will grow up to the end of the research. But for now, we have 9,100 examples already annotated. So,
do you have any double annotated examples that you can use for to calculate annotator agreement already?
Yes. The bot is designed in such a way that the first 100 sentences are the same for all annotators. So we'll control the agreement, inter-annotator agreement.
Okay, so but you don't have the numbers yet, right?
That
was my.
But
you do, because it wasn't in the slides. That's why I'm asking, what is the annotator agreement?
Yes, it's currently in progress because
okay.
Now I expect that the final dataset size will grow.
Okay, and one more question about annotation guidelines and prompts that you use. So have you tried, how similar are the annotation guidelines that you gave to the humans and the prompt that you designed for GPT-4o?
If I correctly understand the question, I try to repeat it so we can cross-check. The question is the approach that we use to to write a system prompt for GPT is the same and fully correlates with the approach, with the guideline we provide to humans annotators.
Yes.
It is. Yes, it is.
Okay. And do you have the distribution between neutral and non-neutral classes in your dataset already?
Yes, the dataset is quietly skewed towards the neutral side.
That's normal, yeah.
With the less represented class, mixed, but from the main three is positive is the lowest percent.
Okay, but do you have like rough distribution? Is it like 50 neutral, 50 non-neutral, or?
As I remember, around 20 to 12%, 20% is positive, 33 like neutral, negative, and all of the remain is neutral.
Got it. Thank you so much.
Small fraction of mixed.
And will you be able to openly publish this data set, considering that you have like private access from other researchers to this data?
I think that currently we agreed that the final data set will be published, but we cross-checked this at the finish of our roadmap to ensure that all sites are 100% agreed. But I think it will be.
Thank you.
I still have a question, just to elaborate on the previous question on the data set. What is an average and mean average volume of a document within a data set? The reason to ask is that you mentioned sentences in the first 200.
I repeat the question. The question is about how long text.
How long the texts are on average?
On average, the average length is about 400, 500 symbols. Includes all symbols.
How many sentences? No, just
three, four sentences.
Small texts.
Yes, but
social media texts.
Yes. No, it's mostly comments from Telegram, but it also includes like large posts with 1,000 and more symbols.
And what is your intuition on the distribution of long to short text?
As I remember from our analysis, around 10% of the data can be considered as long, longer than 500 symbols, and the remaining part is this middle size mostly.
So it's 1 to several sentences on average,
yes,
eh?
Yes.
Okay, thank you.
Thank you, Yuri. So we are moving on to the next speaker, Roman Kovalchuk, with his work entitled Multilingual Grammatical Error Correction with Large Language Models. And he's co-supervised by Mariana Romaneshin and Petro Ivanyuk. Oi, sorry, go ahead. Just wait a couple of seconds.
Try again. No, don't switch it on. Just wait for a second.
And now, yeah, it is switched on. A little preamble to this presentation is the following. So the case I'm working on is grammatical error correction for multiple languages. In our case, it is 11 languages, and you may be familiar with a task of grammatical error correction if you have worked with Grammarly. And essentially, the task of GAC for short is to take an original user message, which may or may not contain errors, and make it grammatically correct, and therefore come up with a more refined and grammatically correct output message. I'm advised by Mariana Romaneshin and Petro Ivanyuk. And therefore, I give acknowledgements to both of them. So Mariana is an area tech lead at Grammarly, and Petro Ivanyuk is a data scientist at SoftServe. And also, I express gratitude to EBSUKU for computing resources. And let's start with a bit of agenda. We're going to start with a problem overview, a bit of introduction and motivation, problem settings, and give a little bit of background what is grammatical error correction more thoroughly than I started in Preambula, and what is multilinguality is in itself. Then we are going to discuss related works, which consist from pre-trained LLMs, the data sets, which are available in public, related competitions, which we decided that were relevant to our work, and metrics, which are used in grammatical error correction task. Speaking about our approach, we decided to publish 3 new GEC datasets for our task, to also evaluate them using human annotation and automatical evaluation, which is a more cheaper option and more better. We will explain it why better in terms of we'll explain it later, and we will also underline the planned experiments which we want to partake to cover our research gaps and explain our project deliverables. Speaking about motivation, so multilinguality is an increasingly popular topic not only in GEC, but also in natural language processing. If you have seen model cards from GPT-4o, GPT-4o Mini, O1 or O3 Mini, and the newest model GPT-4 4.5, OpenAI is more and more tending to market them as more capable in terms of their processing power, not only in English, in all of the tasks, but also in low and mid-resource languages. And speaking about GEC, Grammarly recently released a new paper about GEC in multilinguality, so it is not only popular in the natural language processing field in general, but also in the grammar error correction field as well. The next point is GEC competitions. Recently, NLP4Call workshop hosted 2 multilingual GEC competition in the last 2 years. They are called Multi-GEC 2025 and Multi-GED 2023. Relating to speaking about the problem settings, we have identified the following gaps. So the first one is data collection challenges. The second one is the data usage challenges. And the third one is a derivative of first 2, is low solution performance in a multilingual setting. So speaking about data collection, in a GEC task, it is very hard to combine with high quality data because it is rather expensive, because each individual sample has to be human annotated, and a human has to be very knowledgeable about this task, because he has to know, or they has to know grammatics, syntax, and so on and so forth. So like putting it on a stream and coming by with a lot of data is rather expensive. And therefore, it is difficult to standardize. Usually in machine learning scenarios, we love to have a well uniform data set. So the model is easily optimizable to our wanted goal. And we don't want to have data coming from multiple distributions, because that makes things more hard. Speaking about data usage, lack of data quality versus data quantity ablation studies, we don't know which we want to prioritize when we want to develop a good GC model, more holistic data or more quality data, focusing on more less, but more qualitative, more high quality examples. And low solution performance is a derivative of the first 2 points, because as we observed in the latest multilingual JC competitions, the authors didn't use, like, they didn't generate new synthetic data. They used only the data that competition provided themselves, and they limited themselves by only using an instruction template in English and just training and predicting on the test dataset. So that resulted in low scores and not beating the SOTA for individual languages like Ukrainian. We want to address these gaps by following tracks. So the first one is by publishing new GC datasets, as I mentioned. The second one is by conducting ablation studies on those datasets. And the third point is to utilize techniques from English GC, which is far more technological, I would say, than multilingual, and try to adapt those techniques into our matter field. So the first one is to, our 3 new datasets will be different in quality and quantity. We have one dataset which is like far more quantitative than the others, and that would help us to conduct ablation studies on a matter of which dataset boosts the model more like more quantitative or more qualitative. And we would have that discussion more detailed later on. And yeah, let's move to the next slide. Like if we would take a step back, what is grammar error correction in LLMs? So if we have an original error user message, which may or may not contain errors, we would want to correct that message by using some model. And in our case, we would want to use a large language model trained on a parallel dataset. Parallel dataset is a dataset consisting of pairs of original message and human refined or just corrected example. And training on that dataset would allow us to use that model to correct any user message and help them in their life, like education or conducting or writing emails and so on and so on, so forth. Also, leveraging LLMs allows us to use its take advantage of its knowledge repository, because traditionally in GC field they used more classic models which tended to follow a rule-based structure, like as more grammar, and not take advantage of its knowledge repository and making hard to correct context syntax errors. Yeah, and speaking about multilinguality, as you can see on the following graph, English is far over-researched than other languages like German, Ukrainian, Czech, and others. And although it makes our task a little bit harder, we want to take advantage of this underrepresentation and take approaches which worked best in English and transfer them into our target languages. Speaking about related work, we have 3 tracks which I wanted to underline. The first one is the English GAC. As I've mentioned, we would want to use the techniques which worked best in English and transfer into our target languages. Some methods may be more easy to adapt, and some may be a bit harder. For example, Gactor is a famous model in English GC world. I'm not sure whether you have heard of it, but in a nutshell, it is designed to re-rank possible corrections, but it is trained only in English, therefore making its adaptation a lot harder for our downstream languages, because we don't want to fine-tune other models. And moving forward, multilingual JC is evolving field, and but it contains very few relevant papers. Although, for example, in Ukrainian UNLP Confederation, which had only Ukrainian target language. They've presented methods which are easily transferable to other languages, so making that more relevant to our work. For example, they have a technique of translating original sentence into, for example, German and translating it back, making it more worsening its syntax, grammar, and so on and so forth. And it is easily transferable to other languages, as it is an easy trick. Speaking about multilingual LLMs, we would want to, as I said, fine-tune an LLM, and we are interested not only in its performance in English, but also in its capacity to work, to process other languages. And we ended up on choosing Aya Expense 8B model and Llama 3.1 8B model. And for data generation, we used OpenAI models. Speaking about datasets, MultiGC 2025 is a dataset composed from learners' data and human annotated examples from 12 different languages. And although it is highly related to our work and it is high quality data, it is relatively small because it consists only of 7,700 examples, making it hard to fine-tune a model or conduct some ablation studies. And also, there's three datasets commonly used in English GSC. They all are high quality and high quantity. And we would also use them to standardize our research and like compare our solution to English GSC in a matter of more widely known metrics and datasets. Speaking about pre-trained LLMs, as I mentioned, we landed on AI Expanse and Llama 3.1. The main difference between those two is that Llama usually performs better in English. However, it is trained on far fewer languages, target languages than AI Expanse. So, for example, AI Expanse is trained on 23 languages. 6 out of 11 are our target ones. And speaking about Llama, it is only 3 target languages: English, German, and Italian. However, the Llama, as developers mentioned, it is easily trainable to more languages, but requires some fine-tuning to do that. Speaking about relevant GSC competitions, as I mentioned, there were 2 multilingual GSC competitions, Multi-GSC 2025 and Multi-GED 2023. The difference between those two is that the more recent one contains more languages, but in a nutshell, the methods presented in the most recent competitions are pretty naive, and they limited the top, how do I put it, top contributors in those competitions are used pretty simple techniques and therefore did not achieve such large scores as in, for example, local GC competitions. At the bottom of the slide, you can see UNLP 2023, which hosted a competition only for Ukrainian, but it still holds the SOTA score, although being like 1 year old. And the methods that are laid out there are easily adaptable for multilingual setting. Speaking about metrics, there is a few metrics used in GSC. A few of them are heuristic, and recently there is a trend to use LLM-based metrics as in NLP in general. 0.5 score is a measure for recall and precision, and it focuses precision twice more than recall because we wouldn't want to overcorrect the sentence, because the theory is that if we would produce more predictions to correct the user sentence, it might contain more errors, and we would want to maintain a similar structure to the original message, and we wouldn't want to like overwrite the whole sentence from original, making more mistakes. Second metric is errant. It also encompasses error type, because certain error types are far common and easy to correct, such as punctuation in certain languages. And the next metric is GLAO score, which is n-gram based, and is also used to calculate the precision of 0.5 score in a GEC. And the last but not least is Carpentier score. Essentially, it measures a context-aware approach to measure the target versus input text. Speaking about our approach, we want to publish new 3 GC datasets. We already collected them, and we will publish them in the UNLP 2025 conference. The first dataset is Wiki Edits, a small dataset of human error corrections made by Wikipedia contributors. But it is a relatively small Reddit dataset, which is scrapped from Reddit posts for 11 languages, and we expect this to be more closely related to how humans naturally type, therefore making it more usable. And the third is dataset is based on UberText 2.0 social corpora. It is a larger dataset which would contribute to our ablation studies. Speaking about synthetic data generation, it is commonly referred as two-stage approach. The first stage, we generate the prompts based on human referring data. We want to combine with 2 prompts. The first one is a few shot prompt for generating multiple corrections for a given sentence, and the second prompt is to aggregate those corrections into one, and therefore making more refined prediction. It is a pretty common technique, and in GEC world, and it is rather similar to technique of MapReduce in data engineering, something like that. So should be pretty straightforward. We would also want to evaluate the data sets we collected in 2 tracks. So the first one is automated evaluation, and the second one is human evaluation. Automated evaluation will be done with GPT models. It is cheap, but it is subjective. SLM is too prone to errors, but it produces uniform results because it ain't biased by different human annotators, different languages, and it is more uniform. And human evaluation is accurate, but it may be subjective to the difference in evaluators themselves, but it is rather expensive. And we would want to conduct an evaluation only in Ukrainian, but for all GC datasets. Speaking about planet experiments, we have already generated the data, and we would want to conduct an experiment for data usage to contribute to our ablation studies. For example, to measure whether a high quantitative data set would benefit GC system more, or high quality data set would do so. Method-based experiments, which would help us to combine with a more capable model. For instance, there is a DPO technique, which is based on reinforcement learning. And we want to answer a question whether that would yield better results than typical LoRa fine-tuning. And the stretch goal is also related to ablation studies. We would want to know whether it is better to have one LoRa adapter for all languages, or to use like 11 adapters for 11 downstream languages, and whether that would yield better results. Speaking about project deliverables, we will publish 3 silver GC datasets. We would want to establish new SOTA score for Ukrainian GC model, and we would want to combine with a competitive multilingual GC model. And we will publish instruction templates for fine-tuning on IA 23 expanse model and Llama 3.1 model, and supplementary research paper. Speaking about future work, we would want to conduct human evaluation for all our target datasets, to conduct a DPO fine-tuning for all languages, because we would have a human-related data, and we would want to compare different techniques for preference optimization as DPO or KTO. And the last is to explore newer base model LLMs, GC methods, and approaches. And one more thing, 10 or 15 minutes of your time will significantly help to in our project. And if you would scan this QR code, you would land on a Telegram group, which is for annotating our examples in Ukrainian, LLM generated examples in Ukrainian. And for top contributors, we have prepared some prizes. So we would be really glad for your help. Thank you.
Any questions?
You just mentioned about the contributors. I'm just interested in annotators. Do you check annotators? Like, because we as humans can also do some mistakes, even in Ukrainian. Just interesting, like, do you double check after the annotators or?
It is in progress. We would combine with this data set of human evaluations. We would compare it with LLM evaluations, and we would conduct more thorough research once we have the data.
Okay, cool.
I believe I have several. I'll start with a conceptual question about 11. How did this number come up?
Slide 11?
No,
languages.
the number of 11.
We
Do you plan to develop a system which is a part of the voice recognition system in the lift?
No, we wanted to develop a system to correct grammatical mistakes in 11 languages, because originally we planned to participate in multi-GC competitions, which had 12 languages.
Okay.
And we excluded only Russian from it, so that's why 11, not 12.
Yeah, that's clear. And, judging by your reaction, you didn't see this very, very famous video on YouTube. Just type in 11 elevator, and you'll understand what is the role of voice recognition system in the lift. And this will be an additional argument for you to remove Russian from the list.
Okay.
Okay, now my second question is, well, it becomes a traditional question, like motivation. Could you please go back to the slide with the table of the data sets, where you have a number of examples, but you do not elaborate on the length of each individual example on average? Is it a small text, a very small text? Is it a sentence, several sentences? Is it a long read, or what is it?
It is a great question, because it is different depending on the data set. For example, in multi-GC competition, it is based on an essays, so original essays to corrected essay. And usually it is less than 600 tokens in length. However, it is different depending on language. For example, Italian texts are shorter, and Ukrainian are shorter, like 400 tokens, and Ukrainian are up to 800.
I do assume that it has to be sentence level examples, because the grammatical error correction works in sentences, isn't it?
Yes, usually it works in sentence-based, like traditional approaches, but the authors of multi-GC competition foresaw like a trend of LLMs, and thought that if LLM would have more context, it would benefit from a richer regional text, like from length, without splitting it into each individual sentences. However, the contributors didn't use it. Like they split it into sentences to fit in the context.
Okay, and the reason to ask this question was that you mentioned your own data sets, including the edits in Wikipedia. Those edits could differ in length, in fact. Yeah. Wiki edits.
Here.
Wiki edits.
Yes, they would differ in length. For example, yeah, there are different sizes. But one interesting point is that they are uniform in languages, so that's what we tried to achieve. For example, the wiki edits come from the same data source. The Reddit also comes from the same data source, but for different languages, and Ubertext is just Ukrainian. And that is different from the original multi-GEC competition because they used human-refined data from different competitions, different sources. For example, there is learners corpora. There is a thing called second language learners corpora. So for example, people learn second language and they write an erroneous message and humans refine them. And for example, in UAGC dataset used in that competition, professional and human annotators were annotating the data. So they are different in their nature, and they're not as uniform as, for example, these collected data sets from the same source as wiki edits and transformed by the same GPT, sorry, not wiki edits, but a Reddit data set transformed by the same GPT model. And but we would assess their like power for GC model by human evaluation and ablation studies.
So thank you. And if you go forward to the immediate plans for future work, there is a number of tasks listed in there. Human evaluation for new data sets, it's a crowdsourcing exercise as far as I understand, isn't it?
We'll see. We'll see. We originally planned to conduct an human evaluation for all target languages in all data sets, but
I mean that you involve external people to do human evaluation.
Yes.
That's what I meant by crowdsourcing.
Mhm.
Then you fine-tune models for all target languages. Then you compare direct preference optimization to something else. Then you explore newer-based model, LLMs, and so on, so on, so on. How many people do you have in your team on this individual project? Now the question is, do you think it's feasible to do all this for master thesis?
No, it is a future work after the master thesis.
Oh, this is
For master thesis, we have this approach, and we already collected the data. We are in the progress of making conducting experiment for fine tuning, and we are going to publish those GC datasets.
So what are you going to defend in your master thesis out of this?
We expect to first the datasets, the model for multilingual GC, which includes Ukrainian.
Do you have these new SOTA results for your new Ukrainian GC model?
Not yet, but we expect to combine with one.
Okay. What is the fate of the datasets? Are they already public? Not yet.
They will be published in conference upcoming conference UNLP 2025. We already collected them, but we need to document them and prepare a paper.
What do you mean by published? You submitted papers?
Will be published.
Have you got acceptance notes from the conference?
We started.
This is not yet published. This is just submitted.
Ongoing work.
Okay. Oh, thank you very much.
Thanks.
Okay, the last presentation for today and for today's last session will be delivered by Vitaly Borodavko. And the topic of his presentation is hybrid tokenization for Ukrainian language. And his advisor is Artur Kulian.
Can you hear me? So, ladies and gentlemen, thank you so much for your attention. And I want to present my topic for this master symposium is the hybrid tokenization in Ukrainian language and their approach for the LLMs. So, yeah, first of all, I want to express my gratitude to the advisor of this topic by Arthur Kulian, and also for support from Mariana Romanishin, Yuri Panev, and Nazari Drushak for supporting in making research about this topic. So shortly about the plan. Firstly, we discuss about the motivation and where this topic came from. Also define some research goals and what the key interest of this topic. Then I will tell something about the analysis of the related works that was previously done by other researchers. We can identify the research gap and also define the key questions and problems that will be asked to this research. Also, later I'll give some vision on the approach to the solution, on how we are planned to get to the results, and some evaluation strategy and the results that are already present for today. So a few words about the motivation. Firstly, we all use some kind of LLMs in everyday life. But we all know that all these language models came from the West world, where the English language is a dominant. And of course, as we know, we can see some performance with Ukrainian language in ChatGPT or even with DeepSeek. But we need to understand that Ukrainian language is underrepresented in all these models. What it actually means that the representation of Ukrainian datasets is much lower than English. And that can lead to the potential drawbacks and non-optimal solutions to the Ukrainian language. Also, it's worth to mention that Ukrainian language is morphologically complex. It has a kind of building block structures. It consists of the prefixes, roots of the words, some suffixes, etc. And we cannot just glue together some parts of the words to create new one. So that's also a problem for this research. Also, the potential interest is in the reducing vocabulary size, because as we might know that vocabulary size directly impact the model itself, and we will discuss it a bit later. Also handling unseen words. So that's one of also a problem, potential problem in the BPE, for example, tokenizers that is highly frequently used in modern language models. Also, it would be good to understand the optimal solution, optimal tokenization for Ukrainian language. And actually, one more problem that is the cost for underrepresented language in LLMs, and we also mention it a bit later. Yeah, so the research goals for this topic is try to find the better tokenizer for Ukrainian language than BPE. BPE is purely statistical, and to train a nice tokenizer for any language, we need to have a massive corpora of data. And often it's a really challenge to collect some data, and using some linguistic sorry for that. Yeah, so about the tokenizer I've mentioned. The second goal is to improve the fertility and vocabulary size balance. So it's actually a problem in the tokenizer when we cannot win in both of them. So we either choose the vocabulary size or the fertility. The fertility is the parameter that actually represents the amount of tokens that needs to represent a single words. And as soon as we decrease the length of the morpheme, at the same moment, we need to increase the vocabulary size to cover the whole text. And also probably if such approach will be a more optimal solution, it can put some foundation in the development of Ukrainian-specific large language models. Unfortunately, we don't see such solutions for now. So here is a list of the papers that was a core for this research. Actually, some of them a key interest because of the explanation of actually new token adaptations for existing large language models. Also, for example, language model tokenizers and unfairness. It's also an interesting topic that we will mention. And important to say that it also has a reference to the benchmark that will be used for the validation and evaluation. So it's worth to start with some terminology, as we use linguistic knowledge to represent Ukrainian language in LLMs. We need to understand what is the Ukrainian language and how it is built. So in general, languages are either analytic or synthetic. Analytic languages is the languages that actually represented as one token per words. So in such languages, words are so static that they can be represented with just one token, and it won't be changed. It completely won't be changed. Another group is synthetic languages that actually consist of the two groups as well, is agglutinative and fusional. Agglutinative languages is the languages where one morphemes represent one grammatical feature. Such languages is really easy to represent. It's easy to stack different parts, as during this kind of merging, all these forms inside are not changed. And that's why it's easy to combine them together. At the same time, the fusional groups is a more complex one. It requires multiple grammatical features for one morphemes. And that is why it has different forms. It's harder to segment it, and it has much higher variation in suffixes. And Ukrainian language is actually the example of such groups. As we know, we have a variety of suffixes that can be changed in kind of the same word, but with a different forms. That is why this language is much complex for representation. Some related works actually shows some proofs of usage this morpheme-based tokenization. For example, there was one study that actually researched such usage for Hungarian language, and they actually could get the higher efficient of this model. But as I mentioned, the level of the fertility drops down. That is exactly the example of this trade-off. Also, it's worth to mention that such approach is not stable, even for different languages from the same group. For example, in case of Turkish language, they could reach, they couldn't reach a better performance than baseline model. But for example, in Korean language, that is actually from the same group, they get a much better performance. Probably the key to this difference in the data sets, but unfortunately, it wasn't possible to analyze the approach that deeply. So I guess we cannot be sure that usage of morphological extraction to the standard tokenizers can be really useful for all languages. Yeah, so based on that research, we can do such statement that there is actually no proofs of the optimal tokenizer for Ukrainian language. We know that the most popular models uses either byte pair encodings or subword encodings, but as I mentioned, they are purely statistical. Also, there wasn't any researches of using the morphemes in the tokenizers itself. There is no information as well that is kind of hierarchy in these problems, that as we don't have the morpheme tokenizers, we don't understand actually this impact on fertility. We don't understand the computational efficiency with such tokenizers. And also, we don't know how it can impact on all the past researchers that was done with Ukrainian language on baseline models. Yeah, so what we are trying to investigate is it actually tokenizer can impact the performance? Can we find the actually better tokenizer for Ukrainian language, that one that already exists in the, for example, ChatGPT, that is BPE? Can we actually improve this tokenization process without degrading the model performance? And can we actually reduce the language, the sentence length without impact on the cost of the processing? Yeah, so what we are trying to do with this research is actually described in a few steps. So first of all, we are trying to create such morpheme tokenizer for Ukrainian language. For that, we need to have a database of morphemes. After that, we need to get this database and integrate to already existing encoding process and tokenizers. We want to try to reduce the fertility level and actually keep the vocabulary size as low as possible. And that is why morphemes could be useful as, for example, when we have all the combinations of all the building blocks for creating this language, we can construct any sentences in any forms. And actually, it's an attempt to fine-tune existing LLM models to adapt all these new tokens. Firstly, we need to process some existing sources that contain actually these morphemes, build that exactly vocabulary, incorporate this vocabulary into existing large language models, perform some statistical analysis to compare the byte pair encodings and usage of morphemes in combination with BPE, and just to compare it statistically, is the lengths or is the amount of tokens reduce or increase, or just to give the understanding how it's changed the formulation of the language. And also for better comparison, to understand, is it really can improve language models? We of course need to compare the evaluation of both approaches on some specific tasks. Here is the approach. So firstly, we need the vocabularies themselves. It turned out that Ukrainian language does not have that big library of morpheme-based vocabularies. So there is only a few books that can be found, and they are actually pretty old. So one of them is almost 50 years ago was published, and another one is more than 20 years have passed. So we can claim that this data sets is not the newest, but at least it's something that is already already actually splitted into the morphemes. So as you can see on the right side, this is the example how these vocabularies are structured. So has the first one contain approximately 40,000 words that are split by morphemes. And also the second vocabulary, it has much more words, that is 120,000 of words. That actually can be used for building our tokenization. The problem is that it's just a digital copies, and all these books actually does not contain text layer. So this is the first challenge. So we need to actually parse these books to convert all these knowledges and all these morphemes into the machine readable format. For that, we need to apply some optical character recognition. Here, there is an implementation called Marker. It's the recent implementation that actually was useful, as it really represents some good accuracy into recognizing all these words. After that, as it's really a huge corpus of words that difficult to process manually completely, we used one more step, is actually automated grammar correction with the most popular ChatGPT model. And after that, after reduction of error rate, we applied just some human validation to be sure that the data that we actually collect is representable. Because as we know, bad data on input equals to bad results in the output. So when we have this corpus of morphemes, we are ready to build some tokenizers. So what we actually need to do is to get the already implemented byte pair encoding and ingest these new morphemes into it. And optionally, for further experimenting, we can actually play with the amount of tokens that are present in these vocabularies. We can apply some more byte pair encoding training to create any further merges of existing tokens. Then when we have these tokenizers, we need to apply some continual pre-training. So what's the conceptual benefit from that is that we can have the already pre-trained model. We can incorporate new set of tokens there, and we can start training it to force shift the attention of the large language models from old tokens to new one. So for example, even if byte pair encodings already contain some Ukrainian tokens, we can kind of remove them from the tokenizers and replace it with the new tokens that actually was collected. For this training, we can use I guess the most popular data sets like UberText or Oscar. But all this approach, of course, has some disadvantages as catastrophic forgetting. So when we are actively starting to change the weights, it can actually reduce the performance on the old set, but still not gain the understanding and the usage for a new one. And yeah, and it of course can lead to some overfitting. So for evaluation, we need to compare the pure byte pair encoding that was already pre-trained with the extended version that contains morphemes. The comparison will be in 2 steps. First one is the purely statistical analysis. We need to take the data set. It will be UberText. We need to calculate the statistical representation. So how many tokens it takes to represent the entire data set, the average tokens for a word, or average tokens for the sentence, something like that. Also, we need to take into consideration the vocabulary size. As we know, we cannot just endlessly increase this vocabulary size, as we have a dependency on the model complexity. And if we increase the vocabulary size, the attention model actually increases in a quadratic complexity. And also it's important to track the encoding time, because it's important to omit the situation when we just, when we are trying to reach the better representation, ignoring the reduce in the performance of the encoding time, in the response time, and in the experience in general. And for a comparison of these models, we'll use evaluation benchmark. That is actually, I guess, the pretty recent benchmark that is used for language models estimation with Ukrainian language. And also for comparison, non-existent words ratio, that is actually important as we use some linguistic inspired morphemes. These metrics must be reduced in comparison to the purely statistical byte pair encoding that actually has a problem of out of vocabulary words. Yeah, so some early results about the processing of these vocabularies. We could extract almost 18,000 of unique morphemes. So actually, having these morphemes, we can extract the size of the vocabulary for almost 18,000. And as for now, it requires on average 4 morphemes to represent one word. Yeah, so here is actually the distribution. So as I mentioned, the average is 4. 4 morphemes takes to represent one word. The lower value it requires to represent one word is the better, as the more information is encoded inside one token, the more information can be processed by large language models in the range of the attention window. Yeah, and here is some word cloud where you can see the top most frequent morphemes that was extracted from all these corpora of words. And I guess as expected, we can see that the major part from this is some suffixes or some endings, and we can actually see that they are splitted with some linguistical sense. And here is an example of how different language models can split the same sentences in comparison to how it is split by morphemes. We can see that the key interest here is the number of tokens. For example, with Ukrainian morphemes approach, it is 40. At the same time, we have a pretty big Mistral language that also splitted all this sentence into tokens. We can compare it and actually see how they are different, how actually morphemes are splitted by roots, by prefixes, by suffixes, and how pretty much more randomly it happens in other models. To be honest, for example, if we can see at the JAMA model, it is very close to the actual representation of the morphemes, and it's really preserved the much lower amount of the tokens for sentence representations. And yeah, for now, that is all the results that is present. The next steps will be the actual models pre-training and the comparison of their performance on the benchmarks, and formulating the statistical comparison for having the complete picture of the impact of these morphemes on the LLMs. That's it. Thank you so much. Maybe you have some questions or clarifications.
I don't see.
Look to the right. I have some. Could you please go back to slide number 13? If you look at the last column here, and if you look at the word abbreviatia, is it a deliberate mistake here?
Could you repeat which one?
This one, abbreviatia.
Yeah.
Yeah.
So actually, that is an interesting question, and that is how some separate cases is represented in this vocabulary. So,
це саме ось тут в абдукції.
Yeah. So this kind of J that is strangely presented in all this vocabulary is actually represents the sound that is equal to U in Ukrainian language. And I guess that's because all these vocabularies are pretty old, and this is how they are structured. So you can see that, for example, abdukция, the word, and the morphemes actually splitted the letter ya, that is actually represented as ya in kind of writing formats, I guess.
So now the question comes.
What?
Can you trust these vocabularies?
We
have just a tiny sample in the left and tiny sample to the right, and we found things that could not be found in terms of the alphabet in such way.
Yes. So actually,
could these dictionaries be used in modern settings?
Yeah. So actually, this vocabularies was verified by the experts from the University of Shevchenko. We had a meeting with them, and they gives their, I guess, a professional view on that. And this literature also was verified by them, and they, I guess, in their opinion, they are represented and they can be used for this task. Yeah.
Just imagine that you use it for a Ukrainian tokenizer, which is based on the use of one-letter tokens, like symbols. There are no such symbols in Ukrainian alphabet. How would you use it?
They actually was replaced.
Okay.
So
okay.
This
so
is
you post-processed after.
Yeah.
Okay.
That is why actually the layer of using large language models was used, and after that was some manual validation. Because of course, theoretically, some J's and other sounds can be used in large language models, but such cases need to be handled, I mean, on post-processing. For example, we can generate some tokens with J's, but we need to replace them explicitly after that. What actually can add additional place where we can fail, where we can, I guess, make a mistake, yeah. So that is why all these J's and the following sounds, they actually was split into the actual represented letters, like yeah, like you.
How can you guarantee that this post-processing removed all potential mistakes from this vocabularies?
It was manually validated.
By how many experts?
Currently by one.
That's not reliable.
Well, actually, with some additional searches and automated replacement,
okay.
wasn't
okay.
That big of the issue. Yeah, in perfect scenarios, we need some more people to reduce the, I guess, the probability of the mistakes. But also,
well, to make it more reliable, I think you have to use at least 3 to 5 people to do the same work and to make a sort of an average.
Yeah, definitely. But also, on top of this, pre-processing, we did the statistical analysis. We did see the distribution and the unique, actually the unique morphemes, one of the 17,000, and just to additionally verify that they are correct. Because, for example, if there is some mistake in the OCR, yeah, we can see it, I mean, by eye, for example, taking a look at 17,000 of words instead of 120,000.
That's fine. May I proceed with my next question? Now, my next question is about, it's a little bit more high level and conceptual. I do wonder, what is your grand objective on this project? I mean, this individual master project. What are you aiming to achieve in this project?
So actually, we are trying to understand, is there any better solution to tokenize Ukrainian language that is actually used for now?
Okay, how are you planning to verify if a proposed solution is better than the previous?
Can you repeat this?
How would you verify if the solution you proposed based on these 2 dictionaries of morphemes is better off than the previous solution of the base model?
Yeah, so firstly, we want to reduce the amount of tokens that are required for text representation. This is the first metric. And the second one, we want to keep the model performance of using both of these approaches and at least on the same level, or we want this morpheme BPE will this performance even improve further. That is why we are trying to actually compare all these 2 metrics in complex. Because, for example, if we can achieve a better performance with morphemes, but we actually increase the amount of morphemes that requires to represent the text, it won't be the objective improvement. So we need to either improve one metrics while keeping the second one at the same level, or we want to improve both of them.
So for that, you have to have two things. The first thing is a proof that your morpheme database is complete for Ukrainian language, or more or less complete.
Yeah.
And the second is you have to trust the evaluation benchmark.
Yeah.
Do you have both ingredients in your brew?
So regarding the first component, this vocabularies definitely need to be extended, because these words, I guess, it's missing much more words existing in the Ukrainian language, especially for the last 20 years. Such strategy can be used, for example, with a data set like UberText. What actually can be done, for example, we can filter out the morphemes that are present here and try to find the new one in the UberText that is actually a pretty, recent data set that was mined. It contains kind of modern words, and it can actually make additional it can even further extend the vocabulary that was present in these books.
To have this morphemization for the UberText.
What?
You mentioned the UberText dataset. Does it contain the words split it in morphemes?
No, that is why. Yeah, that is why we need to actually filter out the parts from the UberText that are present here, and then to process kind of
the rest manually.
Process the difference between them, I guess, maybe even manually.
So then the next practical question is, how quickly do you plan to manage to do all this?
That is actually the next step in this research is to try to get all the metrics regarding the usage of morphemes on the UberText.
Just let us speak about the current step. You take these morpheme dictionaries, post-processed as basics, then you use the UberText dataset and add more morphemes. For that, you have to employ some linguists as an expert that will split the new words into morphemes. This will take some time. Do you have an estimation of this time?
I'm not sure it can be done, for example, to the master thesis.
I'm quite sure it couldn't be done.
Yeah.
So what are you going to defend in a master thesis?
So on the master thesis, the first hypothesis is, could we actually reduce the amount of tokens for representing the same text with using these morphemes? And second one is actually to show the impact of the morphemes on the pre-trained language models.
Okay.
So to compare their performance.
Okay, thank you.
Okay, so I don't see hand raised in the room. I don't see hands raised from the online audience. So thank you, Vitaly.
Thank you so much.
I think we can call it a day. And I think it was.
I'll call it a day.
Yes. So thank you so much to everyone who joined us online and offline.
And survived till the evening.
Yes, and see you tomorrow.
Or later today.
Or later today. Yes.